Okay, good morning. Welcome to, I guess, the last session of our AI class. And today I'm quite excited to be able to teach you something about LLM, which is a large language model. I mean, I guess by now all of you will probably have heard, a little tool called ChatGPT, right? And then I want you to maybe get a grasp of what's going on behind it, and maybe appreciate a little bit more about the advancement in in machine and natural language processing. Okay, I think it's really cool, and I guess for the past few weeks I've been trying to condense like so much information into this lecture. So hopefully, if I do a good job, then you should be able to at least understand the concept or a little bit of the inner working of this little thing called ChatGPT. Okay. All right, but before we even go to the large language model, I want to zoom back a little bit and kind of frame what the scope of what are we talking about, okay? And in terms of, like the overall topic, that contains LLM, this is called natural language processing, or NLP. So it is another branch of AI, artificial intelligence, again, right? But then this one, we want computer to comprehend and generate and manipulate human language. So actually, natural language processing, there are like two big branches that come out from it. One is computer science, and the other one is linguistics. So we're not going to be talking about linguistics at all, but we want to frame the scope in terms of the computer science. So how do we make like model that actually understand or appear to understand human language, okay? All right, so in terms of the sub area in NLPs, in terms of computer science, there are a couple of things that we can do in terms of language processing. Okay, the first is called language modeling, and this is kind of like the LM part. You may like, we're talking about the LLM, right? But this is the LM part. This is the language modeling. So what do we do in terms of language modeling? You probably have used Google Translate in the past, right? And that is the machine translation. So like Google Translate, okay? And question answering. This is when if you give the machine the context, like a paragraph, and you ask it the questions, then it can give you the location of the answer. Okay, I'll show you in the end, some of the example in Python. Okay, and also text summarization. So again, this one, if you give a long text, then it will just summarize into a shorter or couple sentences. Okay, and also this is probably the one that we're going to focus today. So this is called text generation. And I mean, you can think about ChatGPT as some type of a text generation, right? You ask the question, and then it kind of gives you a lot of text. So text generation, okay? Although, I mean, in terms of the large language model, like this term here, actually encompasses a lot of things in terms of language modeling. Because ChatGPT can do translation, right? It can also do, answer. Like if you give ChatGPT a paragraph and you ask it about the, like extract some answer from the paragraph that were given, it will probably extract something out for you. So it can do question answering. It can certainly do text summarization. I did it all the time, and more things, right? It can do, like image process, like image generation, and a lot of things in there. So language modeling is actually quite capable of doing a lot of things, not pertaining to a particular area in this list. Okay. Another thing that people do in NLP is called speech. So text to speech is something you use a lot, I'm sure, in the past or has come across, right? And nowadays, the speech that are generated by the language model is pretty cool, right? It's pretty realistic right now. And another thing is called grounding. So grounding is a term that means that combining or translating from one human senses to the other senses. For example, if you do text to image, so it's kind of like go from like speech or text to the image, which is the vision, or vice versa. So that's kind of this kind of translation is called grounding. Okay, but again, today we're gonna focus primarily about the text generation because that's something that I guess give insight, like into how the, like model like ChatGPT is working. Okay. All right. So if I told you about text generation, like if you want to model, like so first the task called text generation, in terms of thinking about AI, you have to thinking in terms of tasks. Okay. So if I were to talk about like last week we are talking about the model that can predict the image classification model, right? So if we want to build the model that can predict, class from the picture, then the task is pretty straightforward, right? So the task is like, given a picture, just tell me what's in the picture. So that's, and if you put into the AI jargon, it will be like predict the right label, right? If you label this picture cat, right? If you feed that picture into your model, the model is supposed to give back to you the label, which is cat. And that is, straightforward tasks, right? And then you can even measure the accuracy of the tasks, right? From, from comparing how many times the model get it right, okay? But if I were to talk about text generation, right? What should even be the tasks for the model? Like, what should the model do, and how do we measure like accuracy for a text generation? Okay, so that's something that you have to kind of define first, okay? And there are many ways that you can define the tasks for text generation, but one of them is next word prediction, okay? And the task is like this. If I give the model a set of words, the sky is, right? And the task for the next words prediction is to give me the probability, right? It's actually not the probability, but probability distribution, okay? So a lot of number probability distribution for all the next possible words in my vocabulary, right? So if I were to think about the entire English vocabulary, I think there's about maybe, like 30,000 words in English vocabulary, right? Give me, the probability of each of the word occurring after the sentence, the phrase "the sky is," right? And I guess if the model is doing the right job, then I should be getting something like this. For example, blue, right? I mean, if you were thinking that the next word is blue, you probably on the right track, right? So maybe the model should give me, 7% confidence that the next word is blue, or maybe the 6% confidence that the next word is the, and something like that. But then, like the word that should not be here, for example, red, should be given kind of like the low probability. So that is something that the model should give us. Okay, so this is called the probability distribution. And when I say probability distribution, that means that the summation of all of this should be 1. That's the meaning of probability distribution, okay? This is similar to how we do with the classification, okay? Like, for example, last time we're doing image classification. If you were to predict, an image label, you have to come up with the set of image label, and the model is actually predicting the probability distribution of the label itself, okay? And if the model was able to do this, like given a set of words, if you feed it into the model, and then it gives out the probability distribution of all the next possible words, we call this model the language model. Okay, so this is kind of like the LLM part in the LLM words, LLM terms. Okay, so the language model gives you the probability distribution of whatever should come next. All right, I hope that sets the stage of what's to come. Okay. All right, so if I were to do this, okay, so we're going to start from the basic model. So the very simple model of how to do this, okay, it's called n-grams, okay. So, I mean, this thing has been around for more than 40 years, actually. Like the first chatbot is kind of like based on this type of model, okay. All right, so if I want to find out, like what is, the next, the probability of, the next word, right? What I want to do is that I have to come up with the training example. Like give me a lot of text, right? I go out and collect all the text that I can find, right? And then I try to calculate that probability by hand or manually, if I can say that, okay? So this is P, right? So the P is called the probability of blue, the word blue, occurring if the previous word is the sky is. Okay, so that is the probability, like this number right here, like 7%, for example. If I want to calculate this by hand, or I guess manually, then I just go into the text that I have from my training example, and then I find how many times the sky is blue appear in my training example. Like imagine that I collect a lot of text from everywhere that I can find. I try to find how many times this sky is blue phrase is encountered, okay? And then I divide this number by how many times the word the sky is appear in my training example. This is the same thing as when you were trying to figure out, like if you roll the dice, like how many times did you get 2? It's like 1/6. It's the same thing. Like you get one occurrence of 2 versus there's a 6 way possible that the outcome can be. It's the same thing as when you calculate that type of probability, actually. So as you can imagine that this one, it's quite simple. And actually, we can actually do that in Python very easily, okay? And maybe let's do just that, okay? Okay, now if you go to my code, hopefully you download the code and then put into your Google Drive, okay? I'm going to show you. So I'm going to run this one from, I guess from my Google Colab too. So go to n-grams. And why don't we go to this one, C1. Okay, and if you want to see the full example or the original example, it's this guy over here. So I just adapt his example. Okay, so let's see if I can build a model that can predict the next word. And in this, I guess the training example that we have will be Hamlet. I don't know if you guys read Hamlet before from Shakespeare. I actually read a little bit of Hamlet, but I couldn't remember anything. It's quite difficult. Okay, so let's see if we can, like write Hamlet from the model. Okay, so I'm gonna load some models. As you can see, that we don't even need anything, like AI based. Like this is just regular Python model, like no AI in here. Okay. And I'm just going to run this one. I'm going to explain later, okay? But this one is the kind of like the code that used to run all the functions, okay? Okay, quite long, but I'll tell you what happened later, okay? So here is where we load the data, okay? So first we're going to load Hamlet from the library called NLTK. So this is called Natural Language Toolkit. So another handy tools if you want to go into NLP in Python. Okay, so now that we have run the third command block, you can see where the file is being downloaded. If you go to this icon right here called Files, okay, if I click it here, then you're going to see that there's a file called hamlet.txt. And I can even look at it, okay? If you want to read it, feel free. That's the entire Hamlet in the file right here. So it's pretty long, right? It's pretty long book. Okay, so this is our training example, okay? Next up, we're going to train the model, okay? this is just a function that got defined in here, train the model. That's all, okay? Let's run it. As you can see, that this one is pretty quick, right? That's the thing about n-grams. It's pretty quick. Like even for Hamlet, which is quite long, takes about, I don't know, 0 seconds, like milliseconds to train the whole thing. Like, yeah, it's pretty quick, right? All right, so what's going on in terms of training, right? Essentially, what this thing is doing is go through the Hamlet, the entire Hamlet text, and then find the occurrence of each word. First, it's just finding, you know, like how often you find the first word, just the word itself, okay? So it's called the first possible words. I mean, that kind of information get recorded into the first possible word dictionary. So this is the first data that we're going to use. If I were to, if I were to inspect this dictionary, this is what happened, okay? So this one, I'm just enumerating over the dictionary and see the key and the value, okay? So this one is the first 6 value in our first possible word dictionary. And as you can see that the occurrence, for example, in the entire Hamlet text, the occurrence of the word the occur 0.0001. So this is 0.1%. Okay, you have to multiply by 100 to get the percent. Okay, and the word actors occur 0.2% in the entire text. Okay, and so on and so forth. Right, and you can kind of see, you know, there are words that occur more frequently in the text, and there are words that occur less frequently in the text. So this is just counting the occurrence divided by the entire occurrence of all the words. Okay, yeah, and we can do that pretty fast, right? Mm-hmm. Okay, this is the first words, right? But then we want to go beyond that. We want to see if we find the first word, how often do we find the second word? Okay, so that is called the second possible words. Okay, and if I were to inspect this, you see something like this. Okay, for example, if the first word is the, then there is 0.02% chance that there is tragedy that follow the word the. And we do that by essentially just following this equation right here. We just count the occurrence of things divided by the total occurrence. That's probability for you, right? Okay? And again, if I were to do enter, right, there are, you know, like 0.8% chance that king follow Polonius, Hamlet, and you can see that this one, you know, just straight right from Hamlet text, right, because there are all of these names occurring, okay? And then, I mean, there are much more than this, right? I only plot, you know, just couple words for you, so actually they are quite long. Like if you see the whole thing, there's a very, very long list of things that can occur after the word the, for example, okay? Not just this word only. Okay. But then we want to do further than that. Okay, we want to be even more, I guess, even more detailed. We're going to do another dictionary called transition. Okay, if I were to run this, you'll see what happened. All right. So, for example, this one, I'm not sure. This one is probably from the line number or something, but if I were to look at the word the tragedy, so I look at the two words at the same time, the phrase the tragedy, and there is a 0.2% chance of the word of follow from the phrase the tragedy. Okay, so this is called the trigram. Trigram meaning that you're predicting the third word from the two words. Okay, so there are many, and we can even do more. We can do 4gram. Like 4gram meaning that we do 3 words, and we want to find the next probability of finding the next occurrence. And you can do, that's why it's called n-gram. Like you can keep doing this, and you can be like, if you do 5-gram, then you're going to predict the word that follow 4 words. That's called 5-gram. So that's why it's called n-gram model. You can use the n number. Okay. So in here, I stop at this part because this is called trigram model. I only predict the third word from the following, from the preceding two words. That's called trigram model. Okay, so that's what we're gonna do from this. Okay, and that's it. This is all the things, all the data, the training data, or actually this is all the results that we need from the model. Like with this, we can go ahead and just predict the next word from whatever words we come up with. Okay, right here. Okay, so here this is how we do it. So first we start with the word. Like you can change this one into anything, right? And then this is how many words that we're gonna keep generating. Okay, and it goes through it goes through the loop. So in the loop, it's just gonna predict the next word, and then it put the next word back into the the input, and then it feeds it back into the model to get another output, and then the output get it back into the input, and it keeps doing that until the end of the word length. Okay, so if I were to run this, you can kind of see that it starts with the word V, right? And then the next prediction is do, right? And then I feed we do back into the model and predict you, and then I feed do you back into the model, and it predicts think, although this is like Shakespeare thing, so the spelling is a bit weird. And I feed you think back into the model, and it predicts off. And it go on and on and on until the end. Okay? And you can kind of see that for example, what you can play around with is that you can change the first word, like issue I, right? And then it's actually just change things around, right? And then you can change the length, like if I do, like 100, then it will just print out, less words, okay? And I mean, first of all, you can see that it's, at the beginning, it's doing okay, right? It looks Shakespeare-ish, right? I don't know if you read Shakespeare or not, but I guess you can. I think it looks kind of Shakespeare-ish, right? Even here, right? I shall obey my father, brother. So it's actually completing a sentence in a somewhat grammatical way. So even this, I think it's really cool. Like even just this probability model, like you can even complete, like make a grammatically correct each sentence from this very, very simple construction, okay? But then you can start to see the limitation of this model, right? So after a while, you can see that it can go into like a self-repeating loop. If it gets stuck into like a, repeating word order or something, then it kind of gets stuck in here. And also, you can also imagine that another limitation is that if I were to type something here, the prediction that is here will probably doesn't really remember what I type here. Like something that occur here has no correlation with something that occur here. And that is the theme that we're trying to fix in the newer and newer model, because this is something that is really hard for a machine to do, right? And it's like even for us, right? We know that there could be something maybe that occur at the beginning of the paragraph, right? And then in the end of the paragraph, we have to relate back into the first thing at the first paragraph somehow. That's possible in human language, but this kind of thing is not possible in n-gram construction. It's called context loss, okay? All right, so I mean, hopefully you have a chance to play around, right? You can even do like random stuff like, I don't know, CMU. Probably gonna fail. Yeah, probably gonna fail. Actually, I kind of cheated a little bit because I told, like the way that I generate text is that if I see the words that I don't recognize, I just choose random words from the pool of the entire vocabulary. So actually, this word probably doesn't appear in Hamlet, right? So whatever come after it actually gets sampled from the first word dictionary. So this is kind of cheating. Like if you don't want to cheat, actually if you input CMU, then everything's gonna stop because it encountered the word that it hasn't, it's not appearing in the dictionary. Okay, so I'm cheating a little bit so that I can give you, like a lot of text. So usually, if you look into the original code where I get this code from, if I input something like this, then it will just stop. It say like, I don't know how to do this. That would be a more, I guess, stringent response from this type of construction. Okay.
How does it know where to make a point or colon or question mark?
We can try. If I do question mark, it will do the same thing because it doesn't. I don't think if question mark doesn't appear in the text, then whatever comes after this is just going to be randomly a sample from the pools of dictionary, a pool of vocabulary. This is what I did in order to make the model keep going, but the actual model will stop, like maybe like from here. It just, I don't know what to do. Okay, unless there is question marks in Hamlet, I don't think so. I don't think there is. Okay, but as you can imagine, that if you want this model to perform better, you should give them more text, right? So that every word that you input will probably in somewhere in your training example. And that would give the model more power. Like this one is relatively small sample anyway. Okay. All right. So in summary, n-gram is actually pretty cool, right? It's actually cool, but it has limitation. So first, it's just quite specific, right? For example, like I gave you example about the sky is, right? But then what if I have another phrase, the sky was, right? And if the sky was never occur in your text, then the model is kind of don't know how to deal with this. Although, I mean, for us, we know that it's just the past tense of that particular sentence. So it doesn't. It's very specific in terms of like the words that it encounters. It has no way to kind of like it's not flexible enough for human language, basically. Okay. And another thing that is a theme of this today, of the technological advancement, is the context loss. Like for example, as I told you before, the n-gram cannot remember what happened, far in the past because of the way that it's constructed, okay? Okay, so can we do better? Certainly we can. This is called recurrent neural network, okay? So this part is something that I want to do separately, but I don't have time, so I can combine it in here. Okay. So recurrent neural network is a class of neural network. Okay, so it's kind of like it's similar. I guess it's another way of constructing architecture from ANN that you just learned like 2 weeks ago. Okay, but then this one is. It's built to process sequence of data. So this one is pretty suitable for our tasks, right? Because we have sequence of words, and we want to generate the next word. So that is why RNN is quite nice for this kind of tasks, okay? So what it's doing is that it's maintains something called hidden states, okay? So remember this term, okay? We're gonna be talking about this one a bit more. So hidden states, it captures information about the previous time steps. So as you can see that this one is the mechanism that address this particular disadvantages, okay? Because it kind of it can remember what happened in the past through the construction or through the way it's called hidden states. Okay, so that's kind of like the novelties in here. Okay. And then, yeah, so essentially you can think about RNN as having a memory of previous input. Okay. Okay. So I like the way that this one is presented. I copied this one from Stanford University lecture. Okay. So the way that they are presenting is like, you remember the neural network, right? The neural network is like this. Something go from the left as an input. For example, like flower, like iris flower, or like house price, right? And then there are layers, or like neurons, right? It's just a function essentially, and then it output things into the output layer. So in the output layer, you either get the probability distribution of classes, or you get just a number. If you want to do regressions, right? It goes from left to right. Okay. So in RNN, we're gonna turn things 90 degrees. We're going to do it like this. So something go from the bottom and go out at the top. Okay? So why do we do this? And not just like this. We're going to do recurrence. So recurrence meaning that things are happening, repeating. Things are repeating. So these are not separate neural networks. These are the same network, but there are things that going back into itself in a loop. This is a way that we kind of unfold the loop, but actually this is the same network, okay? And then what we're going to do is we're going to do something like this. So think about this. These are the same networks, okay? So the input go in at time 0. You're going to split out the output at time, maybe I should use my, here. Okay, so the input goes in at time 0, x, right? Something happens in here, and then the architecture is not like this exactly, okay? It's different, okay? And something goes out at time 0, so this is called y at t0. But then there is something called the hidden state. Remember, the hidden state is like a memory. So there's a hidden state coming out to the right at time 0, okay? And this thing goes into the network, right? And this is the same network from this one, the same thing, but then at time equal to 1, okay? So at time equal to 1, the network is going to be receiving two things, which is the memory from the previous time step and the input from the current time step. And then it's going to do its thing, calculations, and then it gives out the output at times equal to 1, right? And then it's going to output another hidden state at time equal to 1, and that's the memory. And as you can imagine that the hidden state at time equal to 1 kind of remember what happened in times equal to 1 and time equal to 0. That's the mechanism for memory. Okay, so that's what we're trying to fix, right? The context lost, okay? And again, at time equal to 2, the network's going to get the hidden states from time equal to 1 and also the input from time equal to 2. And then it's going to output y at time equal to 2. Okay? So essentially, if you stop here, right? And as you can imagine that the input is like the sky is, right? Same thing that we were trying to do before, right? And hopefully the output is blue. That's how it works. Okay, and again, you can the output from y can be either probability distribution for classification, or it can be just a number. Like you can even do this type of model for like time series, and people have done that for a long time. Like if you might have heard LSTM, that's like a couple years ago, it was still popular for time series forecasting, but nowadays it's transformer based now. Okay, but I digress. Okay. Let's see what happened in some of the results that I found. Okay, so first I'm going to show you the actual diagram that people has. If you look online, you see something like this. This is not what I want. Okay, is this the one? Oh, actually, this one. Hold on, I want diagram. Oh, this one? Interesting. It looks as, wait, what? Okay, so the hyperlink is wrong, but actually the actual text is correct. So if you left click, I think it goes into a different, yeah. Okay, so sorry, when I copy copy the text, the hyperlink is wrong. Actually, I just need to copy this thing and paste it into the browsers. Okay, but I'll remove this one later. Okay. Anyway, what I want to show you first is this one. So this is what you're gonna see if you like look into internet, like on internet and textbook. This is what people do when you do the RNN. Like you can see that the loop, right? This is called the I guess, the recurring, that's why it's called recurrence, right? It's repeating. So the output or the hidden state is going to go back, and then with the new input, and then giving you the output, okay? So, and then if you unroll the loop, you're going to see something like this. Okay, so that's the diagram that people usually do with RNN, okay? Okay, so I want to give you a little bit more information on this. So this is a pretty nice way of visualizing with animation. So hopefully this one will be more easier to understand, okay? So I'm going to go to the very last example. Okay, let me see if I can, I don't need to blow this up, okay. So first, in RNN, okay, there are weights, okay. If it's a neural network, it has to have some weights, right? And weight is like parameter that you're going to train when you, when you want to actually like learn something, right? So we're not gonna go through the training, but we're gonna go through the inference, meaning the prediction itself, okay? And this is the network that's gonna predict the probability of 1 and 0, okay? So it's going to learn the sequence of 1 and 0, and it's going to predict what happened next. That's what it's going to do, okay? And if I were to hit play, then you can see, the weights that are available in the RNN, okay? So for example, the box in here is the network, right? It consists of many, many weights in here. For example, there are this weight, it's called input weights, okay? These are parameters that I should stop. Sorry. Go back. Okay, I want to stop here, okay? So there are many things that the RNN kind of store in terms of the parameters. So first there are U, okay? This is the parameter. There are W, and these are biases. And there are V, and then the biases. So U, W, and V are parameters inside the neural network per se, okay? And X is the input, okay? And then the input is the probability of a certain, I guess the one hot vector, right? So if the character is 1, you're going to have 1 in here. But if the character is 0, you're going to have 1 on the first element. That's all it's doing. It's the one hot encoding version of the word 1 and 0, okay? And then it goes into the network. And these are the hidden states that come from the previous time steps. So assuming that we have some previous time steps, if we don't, we just initialize something or just 0, that's fine, okay? So you do have the hidden states, and you have the input, which is the one hot encoding of your words, right? And then something come out, so these are the Y value, okay? If you want to keep predicting, then you go on to the next cycle or the next recurrence. Okay, so that's the next one. Again, the hidden state goes into here, the new input goes here, and then the output goes here. Okay, and then it keeps repeating that until until the end of the input length, the sequence length. Okay, something like that. Okay, I think I should stop at the end, and I'll explain to you what happened, okay? Okay. So there are four steps in the loop, okay? All right, so at the end, so in here, what we're doing is that given the 4 character, right? 1, 1, 0, 1. What is the probability of predicting the next word, okay? And that probability is this guy right here, P, okay? So P is 0 and 1, so that means that the next words that will come after this 4 character sequence is 1. That's what it's doing, okay? The detail, you don't have to, we can skip the detail, but I just want you to kind of get the idea of when you input something, you input the one hot encoding version of your character, and the output is actually the probability distribution of that. So this is essentially the raw value, but you can put that into like softmax or something, and then you get the probability of the next word occurring, which is 1 in this case, okay? And that's pretty cool, right? I mean, this one is quite a novel idea when it comes out. And then this kind of, like RNN, it's actually used in Google Translate, a couple years ago. It actually works pretty well, okay? And let me show you the actual one. So we're gonna see, okay, so why don't we go into my code? So this one is called recurrence, okay? And we're going to do the same thing. We're going to have the model that trained on Hamlet. And then we're going to see if it's going to spit out something better than n-gram. Okay? This one. Okay, and then the source is this one. So I use this code, and then I adapt something for the Google Colab. Okay, as you can see that if we were to do the RNN, and this particular one is called LST. So maybe I should go through this one first. Okay. Okay, oh, sorry, I forgot to tell you about this one. So RNN is the kind of like the basic architecture for this recurring neural network, right? But then there are many things that come afterward, especially trying to fix the problem of context loss. As it turns out, the vanilla RNN is still quite bad at remember things. So people come up with a new thing. For example, LSTM is probably the state of the art in the RNN world. This one is called long short-term memory. So this one has a special, has different type of hidden states. There are like short-term memory and the long-term memory. And then it can remember things that occurring further in the past. So this one is quite nice, and it's been using a lot in forecasting actually. And this LSTM is a bit heavy computationally, so people come up with another one called GRU. It's called Gate Recurrent Units, okay? Without going through the detail, all you have to know for now is that there are many variants of RNN. And in the code that I show you today, it's using LSTM because that's kind of like a better version of RNN. So we're not using the basic RNN today, okay? If you want to read more, you can follow this link and just scroll through the information, okay? All right, so in the code, we're going to be using LSTM in order to learn on Hamlet again. And here we are using TensorFlow. Okay, so this is the library for neural network training and predictions. Okay, and the rest is the same. So let's load it. Take some time to load, okay? Okay, all right, so if you're done with the first block, can you do this with me? Because RNN actually takes some time to train. It takes me about 10 minutes in my laptop. So I don't want you guys to wait 10 minutes just to see the example. So can you do this with me? Goes into this icon, right? You should be able to see something like this, right? If you go to, I don't know if you download my folder. Okay, if you download my folder, there's going to be a file called the model that has been pre-trained. So for example, if I go to my code, do you see something like this, RNN? There's a file called model, 2025 and whatever. So that's the name of the model. So if you download it onto your, can you download this one onto your desktop or whatever? So for example, I have this file in my local storage, right? I have this one, RNN, right? No, not this one, this one. So say you download that file into your computer, then can you find it? For example, I have it in here. The file is called model. Okay, I want to make this bigger, but I don't think I can. Okay, like model. Okay, so I'm going to drag this file so that I don't have to train the model from the beginning. So I go here, right? And what I can do is that I can drag the models in here. You see that? So if you have the file called model-2025 or whatever, just drag it in here. And it's going to say that this file is temporary. If you close the window, the file's gone, which is okay. And right now it's up. Essentially, what you're doing is you're uploading the pre-trained model onto Google Colab so that we don't have to train from the beginning. You don't have to wait 10 minutes. Okay. Okay, so I'm done. You see that I have this file in my Google Colab. So keep in mind that this file is actually on Google server. If you were to close this, this tab, then everything here is gone. Okay, so you have to re-upload again if you reopen this file. Okay. All right, so if you have this file up and ready, then you're ready to go because you don't need to train it. You just need to use it. Okay. Okay, so let's do it. So first, I said that so right here, it's saying that it's train mode is false. So that means that we're going to load the file from the save file. If you do this, you say the train mode is true, then it's going to train, which takes about 10 minutes. Okay? If you want to retrain from the beginning, feel free to do so at your own time. But at right now, I'm probably going to set the train mode to false so that I don't need to retrain it. Okay? Run it. Okay. And this one is loading the data, so loading the Hamlet.txt, okay? And again, if you were to go back here, you should see Hamlet appearing again. It's loading the file, okay? And then this one just showing the first 10 lines in the Hamlet text. So that one, you can verify that is actually Hamlet, okay? All right, so first it's called tokenizer. Okay, so this one is going to be, I guess, the steps that also occurring in the later model. So first we can do tokenizer. Let's see what tokenizer do. Okay, so first tokenizer is like a class that you instantiate, like the model in scikit-learn, but this is from TensorFlow. Okay, and then the tokenizer is going to fit on the text. Okay, and what it's going to do is that it's going to give the text each word a number. That's called tokenizer, okay? And right now, in the entire Hamlet text, there are 4,818 words. And each word is going to get a number between 0 and, I guess, 4817, okay? So let's see what it's doing, okay? So I can see, I can enumerate, look into the tokenizer itself, and then I can see what word get what number. For example, if I were to use the word the, then the tokenizer will assign the number 1 for that particular word, okay? Because you have to remember that neural network doesn't know about string, right? It only knows number. So if you have text, you have to convert the text into number in some way. And this is the way that we convert text into number by assigning the number. For example, like that. So this one is arbitrary, right? You can retrain the tokenizer to get a new way of assigning number to your words, like that, okay? But as you can see that once you use the tokenizer, you better use the same one every time you come up with the new text, right? Because then if you use the different tokenizer and it assigns the new number to the same text, then it's going to mess up the prediction, okay? So that's the thing, okay? So tokenizer assigning number to the words, okay? And then this one goes to, like this, this number. So for about 5,000, there's 5,000 words in the text, okay? And the next we're gonna create the training example. As you can see that these are essentially from the text, okay? So as you can see that, you can kind of look into it, right? So 1 is the, right? And then 687 is probably something in here, like the tragedy. So like the 687th word is probably tragedy, okay? 4 is probably off, right? Off here. And Hamlet is probably 45, but I don't have it here. Something like that, right? So as you can imagine that this is how we turn the sentence into vector, right? So this is the tragedy of Hamlet, the tragedy of Hamlet by. So the way that we do this is that we give the model a different sequence length, and in each example, we want the model to predict the next word, right? This is the training example. For example, if I give the model 1 and 687, the model better predict number 4. That's how the training example is done. Or if I were to give 1, 687 and 4, the models better give me 45. That's how we construct the training example, the training sample for the model to train. Okay. All right. So this one is just saying that how much do we want the sequence length to be? So if we keep constructing this, then it's going to go on and on, right? But we want to cap it into a certain sequence length. Okay. So we kind of cap everything into 14 sequence. That means that we cannot input the words. We cannot put the sentence that has more than 14 words in here. If we do that, we're going to cap off the beginning. That's how we do it. And actually, this type of sequence length is called the context length. It's a number that's actually used in this model and also in the model that follow. Like even ChatGPT will have something called the context length. And if you're on the free tier, you might come across the fact that if you put the long text into it, it will say that you cannot do it. And that's limited by something called the sequence length. Like that thing is actually valid even in the the later model, okay? But it's quite large for the current like ChatGPT or Gemini. It has a huge ridiculous sequence length. So if you're on the paid tier, you probably would not run into that limitation. It's like huge, like a million sequence or something. Like it's ridiculous, okay? All right. So what we can do is that these are vector that has different length. So this one is not suitable to put into our model yet. So we're going to do the padding. The padding is when we just make sure that everything has the same length. As you can see that we're going to put 0 in the places that, that has no words into it. So in here, I construct the vector that has the element of 14 elements into the vector, in the vector. And I just want to make sure that all the words that are, that I want are pushed into the end. It's called end padding, okay? And then I'm going to create the label, okay? So this is my X, right? And then this is my Y, okay? So essentially, we are predicting, if I give the model 1, so the first vector, right, 1, the model should predict 687 number, right? If I give the second vector, which is 1 and 687, the model better give me 4. And it goes like that. So this is my Y vector. This is my X vector. Like you can kind of see that these are similar to what we do in ANN or even in the classification model. Like even like back into when we do like iris flower. This is the same, essentially the same thing. X and Y, same thing. Okay. And then I'm going to convert Y into categorical. So this one, I want to do one hot encoding of this because this one is actually, it's not suitable yet. So I want to convert even number 687 into one hot encoding of that. So as you can imagine that this number is going to get turned into a series of 0 with 1 at the position 687. That's called the one hot vector. Okay, so that's kind of mimic the probability density that I want so that I can do like the loss and everything like that. Okay, if you don't have to understand this for now, but just kind of see that there are process that you have to do in order to turn everything into a uniform size vector, because the model is actually expecting the size of your input and output to be the same, and that's why we have to do something like this. Okay, and then this one from scikit-learn, train test split. Okay, I'm just running the split data. Okay, and later on I'm creating the model. So these are the models that I create. So as you can see that there are LSTM. So these are the highlight in this model. So LSTM is a recurrent neural network. Okay, the rest is kind of similar to what we did before. You have dense layer, and you have embedding. We'll talk about it later, but the highlight of it is this one, LSTM, okay? If I were to run this, you can see that this model is pretty huge. I guess I should run, where is it? Why is it not running? Create the model. Oh, okay, because I'm not training the model, okay, so I didn't build it. Okay, but I keep on running and you'll see, okay. So this part is when I load the model. I guess this one will be, I can show you this one. If I load the model, you can see that this model is actually quite huge. There are about 6 million parameters, right? I remember that the last time we did CNN, right, and then we go to about 200,000. So this one is much, much bigger than we had before, 6 million, about 7 million parameters, okay? And if you were to run this, okay, if you set the train mode to true, it's gonna run the example. It runs about 10 minutes, okay? But we're gonna skip everything because you already have the file, so you can load the pre-trained model, okay? So why don't we play around with this? So this part is when we do the prediction of the next word, okay? So right now, this is a function. I'm just running it. And then lastly, you can kind of play around with this one. Oh, okay, I wanna show you this one. So how does the model work, okay? So this is just the run through of one prediction in terms of all the steps, okay? So then you can see what the model is doing, okay? So I'm gonna run this one and show you line by line, okay? Okay, so first, if I were to give the model the term with mirth the king, so that's 4 words, right? This word's gonna turn into the token number from the tokenizer, right? Okay, and then because this one is not yet pad, right? We're gonna pad into the sequence length of 14 because that's what the specified length of the sequence input, right? So I'm gonna pad this thing with a bunch of 0, okay? And this is gonna be the input to the model, okay? And the model is gonna output a bunch of number for me. Notice that this number is actually, this vector is actually quite long. This is going to be 4,808 elements long because this one gives me the probability of all the probability of the next word occurring in my entire vocabulary. So this one from my tokenizer. So all I have to do is I have to find where is the maximum location in this, right? For example, my maximum location is 5, okay? And I looked up into where the tokenizer to see what is the 5th word in my vocabulary, and that is the word I. Okay, so that's how the model is predicting the next word, okay? Essentially giving me the probability distribution of the entire vocabulary, okay? I got the word I. Okay, so that's one step, right? But I can repeat this step. I can put I back into the input sentence, feed it back into the model, and the model is going to output another word. And I feed it back here and get the whole thing running, okay? And by doing that, that's exactly what I just did right here, okay? So in here is when like if I say I am, right, and then I can just run the whole thing like that. Pretty cool, huh? So that's RNN for you. Okay, and if you want to change the number of words that it gets predicted, you can change the number in here. So right now I set into 150 words. You can make it longer or shorter as you wish, and you can also change the input text too. You can make it input text a sentence too, because the models actually know how to split the text according to the space. So this is not like Ngram where you only put one word as a seed right now. You can put as many words as you want in here. The tokenizer will take care of splitting words, put into the padded input sequence, and then get the prediction out for you. Okay, so feel free to try around to see, and you can and hopefully you're convinced that this one is actually better than Ngrams. Right? I mean, much better. Although you can kind of see that there is doing something weird here. I don't know why. Like it's getting very a lot of very. But it's producing a somewhat coherent sentence. It's pretty cool. I watched the Stanford University lecture, and and the text they given them is the math paper, and the model is actually output like the math paper. This is pretty cool. Like it has like lemma and like all of this math stuff, pretty cool. And then I think they also do like academic paper, and this model actually write academic paper that if you read it, it doesn't make sense in terms of like the actual material, but like the word itself sounds academic enough. Like, so essentially, if you change the text, not the Hamlet, you can put anything like, for example, like your paper into it, and then model is gonna predict something or write something that mimics what you're writing. It's pretty cool. And the thing about the neural network is that if you put in the words that doesn't exist in your text, it can actually do something with it too, because it's essentially inside there will be the token that's called unknown, but then that unknown token actually will produce the next word prediction for you. So I don't even have to tweak anything. I just input random things into it, and then it's gonna output me something from that unknown token. There are also unknown a token in your vocabulary. So you can even just input weird stuff into it, and then it will work too. Actually, it even works in Thai, but Thai is especially difficult for tokenizer, because in Thai language there's no space between words. So there you have to use the special tokenizer. It's called Thai tokenizer. It's possible to do, but I don't have time to do it, so I couldn't show you today. But probably like German, English is fine, but Asian language is particularly difficult, like Chinese and Thai and Japanese. It's quite difficult, but people have solved it already. For example, like in Thai, there are organizations, NASDA, Uttayan Vittiyasat, they have the units that actually work in this AI Thai language processing. And the Thai tokenizer was developed by Uttayan Vittiyasat. So yeah, we already have it already, so you can do Thai language. Okay. Okay, shall I go on? You play with it. So as you can convince that this one's better, but it's not the best, and it has some limitation. Okay, so let's see what it's not good at. Okay, again, what it's not good at is context loss. It's better than Ngram, but it's not best. It's not good enough for human language, because in human language we could have something that occur in beginning of the page, and then 10 pages later we might want to have that information be relevant to what we want to predict, and that's not possible with RNN. Okay, so that you still have some context loss, and the term is so prevalent that this problem is so prevalent in RNN. There's a term for it. It's called vanishing gradient. Okay, if you want to have more, if you want to look up for more information on context loss in RNN, look for the term vanishing gradient. Okay, that's something that occurs during the training. Okay, and another thing is that when you do things sequentially, you're going to run into the problem where you cannot do things in parallel. And like GPU architecture is very good at doing parallel computation, but RNN architecture make it so that you cannot utilize GPU capability as well. So that's another limitation that's huge limitation actually. Okay, so we wanna fix that. Okay, with the last architecture or the hottest, I guess the hottest things right now in AI's world is called transformer. Okay, so that is, I guess, the novel, like the state-of-the-art sequence, I guess, sequence processing model. Like transformer it's not only used in text generation or in language. Nowadays, people use transformer for forecasting too, and also vision too. It's pretty cool. Okay, so what is transformer? Okay, transformer is a type of neural network. Again, neural network architecture, but it's very, very good at processing sequential data. Okay, so language is one of them, but time series another one of them. Video is another one of them, right? There are many things that occur in sequence, and this is pretty cool. Okay, the thing that makes transformers so good at sequential data is a mechanism called self-attention. So this is the crux of the whole model. So if you understand attention, you understand why the current model, like language model, is so good. It's because of the self-attention mechanism. So hopefully today I make you understand a little bit more about self-attention. Okay. All right. So when we do transformer model, I just want to let you know that there are many types of it. Okay. There are three main types of transformer models. First one is called encoder decoder. Okay. So that's for language translation. Okay. And so the translator that I use today is probably come from this encoder decoder transformation model, transformers model. There are encoder-only model, which is called BERT. I guess the most popular one is called BERT. It stands for bidirectional encoder representation from transformer. Okay, but today we're going to focus on the version of transformer called decoder-only, and the most popular variant of that is called GPT. I mean, I guess GPT, right? ChatGPT is the decoder-only transformer. Stand for generative pre-trained transformer. Okay, so keep in mind that there are many types of it. Today, you only look at this one. But if you understand just one of this, the rest is actually quite similar. Okay, so hopefully, I can make you understand a little bit more about transformer. So GPT today. Okay. All right, so there are many resources that I use in order to come up with this lecture, but so feel free to explore this and also a bunch more on the internet. There's so many good resources now today, but what I want to focus on is this one. Okay, so what you're looking at right now is the inner working of GPT-2. So GPT-2 is the older model from ChatGPT, and it's open source, so people have looked into it. But GPT-3 is actually closed source, so we don't know what happened, so we cannot do anything with it. So you only look at GPT-2, okay? So first, I want to show you this. So this is what happened when you give the model data visualization empower user tool. So that is the input text, okay? And the model is actually going to predict the word visualize. So I want to show you what happened inside the model in order to predict the word visualize. Okay, so that's the task here. Okay, okay, maybe I can zoom in a little bit. Okay, so first you can see that there are words. I mean, I guess the phrase is broken down into words, and that's from a tokenizer. Okay, if I were to look into this, there's something called embedding, and I haven't told you this one. Actually, we already use embedding in the RNN, but I just kind of skipped that. But I want to show you from here. Okay, right here. So first, the tokenizer is going to assign a number. For example, the data get assigned to ID 6601. Okay, the word visualization get assigned to this particular ID. Okay, and if I remember correctly, there's about 50,000 actually, yeah, 50,000 vocabulary in GPT-2, okay? Okay, but actually, what happened is that not only is the word get assigned the number, it's actually get transformed into something called embedding vector, okay? You can see here that actually data goes into number 6601, and number 6601 get transformed into a vector that has the length of 768. This particular number is the number that is used in GPT-2. Okay, so you can imagine like this, right? If I give just a number like that, associating with the words, that's okay. But actually, there are better way to do. If I were to give a vector representation of the words, I can make it so that these words actually have certain directions and they have relations that you can kind of tune around. For example, if you look into this embedding vector, what it's doing is that it's gonna make it so that words that have similar meaning will be closer to one another. For example, like man and woman will be closer than man and cat, for example. Like the representation of the words in terms of vector space actually give the words more meaning. That's why we embed it in the embedding space, okay? And this embedding space is very large, right? It's 768 dimensions. So there are plenty of room to make sure that all the words do have special relationship in terms of the vector. Like you can also add vector, subtract vector, and also find the cosine angle between vector too, to see, you know, like the words are similar, has some certain relationship to one another. So this one actually gives the model more room to, I guess, to interpret the words, associating with its meaning, okay? That's called embedding vector, okay? That's the first part. Actually, we use this one in our RNN, okay? If I were to go back to see where it is, it's actually right here. Let me just show you real quick, okay? If I go back to RNN, I actually closed it already. I'm just going to open again. If you look into the model, there's actually a layer called embedding, this part right here. So in the RNN model, we actually did the same thing. We turned the vector from the number that is assigned by the tokenizer into a vector that is 100 elements long into the embedding space that has 100 dimensions. We did that too, okay? If you don't do that, then the model is going to be pretty bad. People do this all the time, okay? All right, so that's the first step. The second step is when we do the positional encoding. So this one is kind of like a detail, but then the positional encoding is another vector that tells the model where or the order of the words, because the order of the words is pretty important in language. If we switch around the order of the words, the meaning actually change. So we have to tell the model that there are certain position of order of the words. So that comes from the positional encoding vector, okay? So you can imagine that this data transform into a really large vector, get added to another large vector, and that is the input to the transformer layer, okay? Now I go back. Okay, so when you visualize the transformer layer, I want you to see the whole thing first, okay? The whole thing is actually this part. You see the dotted line? So the whole dotted line is a transformer layer, okay? There are things that goes in, which is the words, right? With the embedding and stuff, right? Goes in. And whatever goes out actually is going to be the same kind of words, but it gets a lot of context information. As you can see that whatever goes in, there are kind of 8 vectors going. Whatever comes out, 8 vectors, okay? And I just want you to see the output first, I guess. So the output is actually going to be calculating from the last vector. And this output is going to be turned into the next word prediction, which is called visualize, okay? I will come to this later, but I just want you to see the whole thing, right? There are things that goes in, 8 vectors, which is the representation of the words, right? And there are vectors that come out. And then we're going to use the last one, because the last one is actually the one that's going to predict the next token, the next vocab, the next word, right? So the last information is going to get turned into the probability density, which if we do the maximum of it, then we get the visualize, which is the next word prediction from the GPT-2 model. Okay? And one thing to keep in mind is that if I were to look at the transformer model, there's actually 12 of the, how many? There are actually 12 transformer blocks in here, okay? So as you can see that there is this dotted line, which is called transformer layer, but you can see that there are actually 12 more, like that, see my mouse in here? There are actually 11 more of this block that are, in sequence. So it's actually, this is quite large. The model is really, really large. Like this thing is huge already, but there are actually 11 more of them before the actual output. Okay, so you can kind of see, like why this thing works so well, because it's so complicated, right? It's very, very complicated. Okay, okay, so we're going to focus into just one transformer block, okay? And then let's see what happened, okay? All right, so first, this is where the magic happened, okay? Let me just show you this one. Yeah. So first of all, there's going to be weights that are associated with the neural network, right? There are 3 types of weights that occur here. There are the blue, the red, and the green. Okay, I just do the color. I think it makes more sense, okay? There are weights that get multiplied with the input, okay? And there's also biases, okay? There's the blue, the red, and the green, right? So these weights gonna transform the vector. So these are the vector that goes in. So this one is 768 dimension, right? It multiplied by all of this and get transformed into even bigger vector. And it has the portion that correspond to the blue, the red, and the green weights. Okay? And the cool thing about this is that you can kind of see where it comes from. Like I really like this one. Like if you do it on your own, you can kind of go through at your own pace and see, how each of the data come from. Like this is so cool. Like I don't have that in my day. Like this is so cool. If I see this, then my learning will be much better. Okay, like that, right? And then all of these are 768. So you can see that this one is 6 times 768. But then in the end, you have dimensions that are increased to about 2500 because you have like 3 parts concatenating together. Okay, so feel free to move things around just to get a hands of what actually happened inside. Okay, I wish I had that in my day though. Okay, and to put into the transformer jargon, the blue part is called key. The blue part is called query. The red part is called key, and then the green part is called value. So query, keys, and value, and you'll use that later. But I just want to let you know that there's a term associating with each of the colors. Okay. All right. So hopefully I have introduced something called key and query, keys, and value, weights. And then whatever comes out will have the part that correspond to key, query, key, and value too. Okay? So if you can imagine that there is this vector Q, K, and V, right? Query, keys, and vector. But actually there are many, many sets of it. Okay? And each set is called head, okay? So when I do this one, so if I click it here, back into here, right? This one is just one set of Q, K, V weights, okay? There are actually 12 sets of this. It's called head, right? As you can see that my mouse here, there's a head 1 of 12, right? So the set of Q, K, and V weights give you one head, okay? So there are 12 head That's called multi-head attention, right? So there are 12 heads, so there are 12 sets of this Q, K, and V weights. And you can see that there are many of them. There should be 12 of it, but right now it only shows 6. Okay, so imagine that there are a lot of Q and K and V matrix, and then each of them will get multiplied to your input and give you the long vector. So you have a lot of data in there. Okay. So next I'm going to focus on just one head. So let's see, I get head 1 of 12, right? I can also go through different head. You can see different things happening, right? When I go through different head, it means that I'm using different set of the Q, K, and V weights. Okay. So right now I want to do head 1 first. Okay. And what happened after this, right? I want to use this vector to get more calculation, which is this one right here. Okay, so let me explain what this is, okay? So in each head, right, each head, you will have 6 vector that is about 2800 dimension long, okay? And there will be parts that have different color in each vector, okay? So the part that is red is called key. The part that is blue is called query, okay? So the key and the query will get multiplied by one another to get a matrix called the attention matrix. Okay, so you can use your mouse to see where it goes in, right? For example, if I go to this particular result, it comes from the key so the red part in the data vector multiplied by or dot product with the blue part in the data vector. Okay. If I move this around a little bit, maybe here, okay. So here is the part where the red part in the data vector is get dot product to the blue part in the visualization vector. Okay, each vector will have 3 colors, right? And then different color get multiplied differently. And you can kind of track down in here, okay? Right? So this one is called attention matrix. Actually, the attention matrix is the one right here. But this matrix is the result of multiplication of the different vectors, right? And this one is called the mask version. So it's called the scaling times the mask. So the mask is essentially using so that the word data does never get multiplied with any of this, because data is the first word. It's supposed to be looking back only. Like when you do the word prediction, the words that are on certain, certain position should actually look back only. It cannot look forward because that's cheating. So that's the reason why we have to mask it so that this part is essentially 0. So there's nothing to do here. It's just this one just allow so that you don't cheat per se, okay? But in the end, you're gonna get something called the attention matrix by doing the softmax, okay? But don't worry about the detail. But I want you to understand that the crucial idea in here is that this part is called the attention matrix. It's because this part is gonna, it's gonna specify how much each word attends to another word in the phrase. That's the part that is very, very important, okay? For example, this matrix tells you, for example, like this line tells you that the word power, right, will attend to the word data about 48%, okay? And the next dot, okay, here, 0.22, meaning that the word power is gonna attend to the word visualization about 22%. And also, it's gonna attend to another word, M. M is also another token, right? It's gonna do the M about 24%. So this attention mechanism essentially allows the words to actually absorb the neighbor context meaning. That's the crucial part in why this thing works at all. Like, think about this. I mean, I guess I need to give you this type of example, right? For example, if I were to do like bank, right? The word bank can mean many things, right? If I say I went to the bank, right? to deposit my money, right? This bank here. And then maybe I set by the bank at the river, right? Okay. You can imagine that the word bank here has different meaning. The one that is actually the financial institution, and this one is like a place, like bank is a like ขอบฝั่ง อะไรเงี้ยนะครับ and if you don't have any mechanism to assign different vector to these two words, then your language model actually failed, and that's what happened in the n-gram and also in the recurrence neural network. Like in all of this previous model, if you were to use the word bank, it gets assigned to the same vector, which is wrong because bank can have different meaning according to the word that gets surrounds it. Okay? So this attention mechanism that used in the GPT is actually really, really crucial because the word bank can absorb or attentive to the words around it and get different vector representation. And that is why this thing works so well. Like it solved the language problem pretty cool, okay? And that is where this thing happened, right? For example, right, the word power will get some like absorbing the context from the words that are surrounding it. So that this is called the attention mechanism, okay? And it doesn't do this one time, it's actually do this a lot of time. Like it like this thing get recycled or it go through like this part so many times. For example, this is just one head, right? Oh, okay, but then there are also 12 of them. So 12 head, meaning that there are different ways that the words can absorb the neighbor's meaning in one transformer blocks, right? But there are also 12 transformer blocks. So they actually do this about 144 times. So that's a lot. That's a lot of calculation. Then that's a lot of the context absorbing. So that's why it works really, really well, okay? And the last thing is that once you do the attention matrix, then there's something called the value, which is how much you want to change the given matrix according to the attention mechanism. So I'll just skip this part because it's not important. But it's actually important, but it's not relevant to what I want to say right now. But if you want to see, you can kind of see that the attention matrix, right? And then it's going to get multiplied by the value and then add into the output parts, something like that. So I'll skip this part because it's get confusing, okay? Right? So this is one, I guess, attention mechanism. And the output from that is actually going to be this part. So the same vector, right? But then it has context already. So the vector that comes out from here kind of knows what happened in the sentence that precedes it. So it's really, really, so like all of this has different representation now, okay? And this is not done yet because this is the attention mechanism. And the next part is called the MLP part. So this one, MLP. So I'll just put into here, okay? Where is it? Okay, right here. So the next part that after attention mechanism is going to go to the multi-layer perceptron. So this part is exactly the same as the ANN that we learned from 2 weeks ago. It's the linear combination of all this input and then time some activation function and then given the output, okay? And this one, as you can see, that it gets expanded into the vector of 3072. And actually, this is actually where a lot of weight kind of falls into. If you remember, if I recall correctly, like GPT-2 or GPT-3, it has about, I don't know, 600 billion parameter. I think more than 60% of the parameters actually live in this multi-layer perceptron parts. So as you can imagine that where the memory or all the knowledge of, like the human knowledge is actually stored in here. Like if you ever wonder like how does ChatGPT know about, you know, like everything, like all of that knowledge is actually stored in this part right here. Okay, not the attention parts, but in the MLP parts, okay? Okay, we're almost done. So after the MLP, then there's something called residual. So I'm going to skip that too. That's kind of like a small point, but it helps with the training. Okay, and then that's the transformer blocks for you. So the attention and then the MLP, and then whatever come out, get to do 11 more time through 11 more attention blocks. Okay, and then the output. Okay, the output is going to be again 8 vectors. Okay. But we are going to use the last one because the last one is where we use to actually predict the next words. Okay? So these are the embedding of the last vector through 12 transformer blocks. Okay? And it gets projected into a more, I guess, a huge vector. And this one is called unembedding metric. It's the reverse of embedding. So it takes 668 dimensions and turns it back into 50,000 dimensions. This one equal to the number of vocabulary in the model. So this one gonna turn into all of this number, which gonna give me the most, I guess, the probability distribution of the next words. Okay? So this one get transformed through the softmax and give me that 50% confidence that the word visualized should come after that whole input. Okay? Just a little things, when you do probability, there is also a term called temperature. And this one, if you look into the ChatGPT or Gemini a little bit more, you're going to see that you can set the temperature of the model. The temperature comes in here. So before you do the softmax, you can divide the whatever number that comes out with the temperature part. So the temperature control how random things are. Okay? Essentially, if you have high temperature, it means that you're going to squeeze this number closer to one another. If you lower the temperature, like this number will be more further apart. Okay? So that essentially what it is. Okay? Okay, and then the rest, you just have to pick whatever the most likely. It's not always the best case to always pick the most probable words. Sometimes you might want to do the top 5, and then you randomly select the top 5 so that when you run the model, each time it actually produces different things. You don't want the model to produce the same thing every time. That's how you sample the probability. Okay. Yeah, so that's the whole transformer thing that has been on the bus ever since 2017 with a paper called Attention is All You Need. Okay? Feel free to change this example to something else, and you can kind of see how the inner working of different things. Okay? Like that if you want. Okay. And now feel free to experiment around with the temperature too, because as you can see that if you increase the temperature to a higher number, then the probability of the words will be closer to one another. So you have higher chance to sample different things. Okay? Something like that. Okay, do play around with it. I think it's a really cool visualization. But I know that by explaining things, it's kind of fast, right? Like this, you have to go through on your own pace. I think that would be the best if you want to actually learn how it works. Okay? Okay, and another one that I recommend if you want to kind of like solidify your understanding of the transformer is this visualization. But I'm not going to go through it because it's kind of the same, but in a different way of visualization. Like if you go through this example, it's actually the same thing that I just mentioned, but in a more, I guess this one is more detailed and actually kind of help you internalize things in a more, I guess, concrete way like that. Okay, but you have to go through by yourself if you want to learn all of this. Okay, but I like this model because it's actually give me the scale of what the GPT like version is. Okay, for example, if I were to stop this, let me stop this one. Okay. I can see that this one is called Nano GPT. So this one is not even GPT-2. It's less than GPT, like it's even less than GPT, right? And there's also GPT-2. Like this one is this big, like so big compared to whatever we have here. Like this one is already complicated, but it's just a small blip compared to the GPT-2, smaller version. And then you can do GPT-3, this is even crazier. So as you can imagine, like why it works so well, because it's so complicated. But the essential building block is still transformer. But it's just so huge that I don't want to go through it, but yeah, you may if you want. I can go through all of this. It's pretty cool, like all of this. Okay. Hopefully you can appreciate like the human effort to do all of this, and then the carbon dioxide that is produced ever since. It's a lot.
It's not renewable energy?
No, this one. I think that if I remember correctly,
Like the servers, you know that?
if I remember correctly, like to train GPT-2, it produces the amount of carbon dioxide as one car running for a year or something like that. It's like crazy. So, but the thing is that once you do all of this, people can actually build on top of it. It's called fine tuning. So if you want to build your model that built on top of GPT-2, you don't have to do everything from the beginning. So it's kind of do it once and then you don't have to do it again, for example. So this is kind of nice way of producing things that are on top of it. Okay, so why not? And another thing I want to show you is this one. So this one is called attention visualization. So give you kind of like the inner working, another way of showing how attention like link the context into specific words in the sentence. Why doesn't it run? Okay. So again, this is the input of the input tokens, right? The girl ran to the local pub, right? And then right here is where the attention occurs. So it's visualizing, it's showing you that there are different layers. So as you can imagine that GPT-2, there are 12 layers of transformer. So if I'm looking at the layer number 1, which is the very first layer, and then I see that there are 12 heads, right? Remember 12 heads, so 12 sets of that 3 color weights, okay? If I were to look at all of this, then I can see, for example, ran in here, okay? So the word ran actually get context from all of these words. So for example, the girl ran. So it's actually doing a quite nice job of figuring out like if the word ran should be, you know, like should get closer or should get some information from all of these words, okay? And you can also see that if I do the word she, her, okay? Actually, this one not right, but if I do maybe layer 2, okay. I guess I would expect the her to get relating to the girl, but I guess it's not. So I don't. When I guess it's doing its thing. Like I'm not sure her, because her should be girl, right? But it's not doing that. I'm not sure why. Maybe here. Yeah, I don't know why. But the rest, oh, right here, right? The word girl get attention to the word her. So it's actually right here. And something like that. So the attention mechanism is actually figuring out like where things should be attend to what. And then that's kind of like the magic behind the ChatGPT, like why it understands you so well because of that type of mechanism. Okay. All right, so it's been quite a journey, but I want to end this thing with, you know, the actual usage of GPT, right? Actually, if you use Python, like you have a lot of tools that you can play around with it. So why don't we go through the last one, transformers, and called Hugging Face. Okay. So first, the transformer, if you, like, I'm not even gonna attempt to train anything today because it will take years in my laptop per se, right?
I tried using the LSTM code. I tried it to read the Transformers 5 script. Yeah.
Does it work?
It works.
It works. Okay, the RNN is, okay.
The text it's writing is like very cheap.
Okay, very cheap. Yeah, RNN is still doable in your laptop, but I'm not even gonna attempt to do transformer training in my laptop. It takes, I mean, for the real model, it takes like $10,000 on cloud infrastructure. So I'm not even gonna attempt that. It takes like a couple months to do it. So it's as crazy as that. Some of the smaller model takes like days to train on your computer. So, but we're gonna use them. And actually, the really cool thing is that there's a library called Transformer by the Hugging Face company that gives you resource to like so many types of transformer model that you can use right out of the box. This is so cool. I just have the time to figure this out for this lecture, and I've seen this a lot, but then I never find the time to use it. But this Hugging Face website, so feel free to look through it. It's quite overwhelming. There's so many things in here, but if you know how to use it, it's pretty easy. Okay, let me show you. Okay, first we're gonna import the model called the library called Transformer. So the Transformer package is written by this company, Hugging Face. Okay. It takes about a minute to download because it's quite large. Okay. And for RNN model, feel free to change the text. Maybe you can change to like German or something. See if it actually produces coherent German. So this one, I experiment with it. It takes about 1 minute to load this library. Okay, 49 seconds. Okay, so in I guess the inner working of it is, I would say that it requires some understanding, some detail, technical detail understanding of how the things work in terms of like Python code and also how Transformer works. But in order to use it, it's actually extremely easy. So I'm going to show you how to use it today. Okay, not so much as to train it, but there is a function, or I guess there's a function called pipeline. Okay. The pipeline is a function that you can use to load any type of models that you want and also the tasks that you want to do. For example, there's a task called text generation, and the model that I want is called OpenAI/GPT-2. Okay, so this is the model that we have been learning. We're going to use it. So I'm going to load it, hit play. And you can see that it's actually have to download. So, and the model is quite large, right? It's about 600 megabytes. For the weights. Okay, there's a lot of things to download, right? And once you're done, you can actually use the model. Like for example, I put everything into the variable called model, and all I need to do is just have to put the text in it, and then just generate the text like that. There you go. Here. It's pretty cool, right? So now, I mean, this is essentially GPT-2 on your computer. So you can use this model to do whatever you want. Like this is so cool. Like if you have to do this in other environments, it's actually quite hard, right? But this one is so easy, okay? So feel free to change anything in here because this is like the earlier version of ChatGPT. So you can ask this model questions. You can ask them to do stuff, but probably not going to be the best. But it's actually running on the local computer. I mean, it's on Google Colab, right? So I can change anything I want, right? I can do like Write Shakespeare. Write Hamlet. Okay. Shakespeare. Okay, and I run it.
How many epochs you recommend for LSTM?
How many what? Sorry?
Epochs.
Epoch? I try about 40. After 40, it doesn't make any improvement. Okay. But I mean, if you change your training example, then everything changes. So for this Hamlet, particular Hamlet example, about 40 is enough.
Okay, I did 50 and probably not enough, right?
50, then 15. Okay, you can do more. You can do more. Okay. So feel free to play around with this GPT-2 version. Okay. And what I want you to do is actually, if you go to Hugging Face/model, so let's try changing the model to see what happened, okay? So we're gonna go to Hugging Face and go to model. And what I want is called text generation. So I'm gonna choose this thing called text generation. Where is it? Where is it? Cannot find text generations in here. Wait, where is it? Text generation. Oh, it's actually right here. So if you click at the text generation icons in here, it's going to filter the model that do text generation. And right off the bat, you can do DeepSeek AI right now. So why don't we do this one, okay? We're going to click in here. And then we're going to copy. You see that little buttons in here? Just copy the name of the model, right? And then I'm going to go back here. And I'm going to change it. So I'm going to copy. Oh, actually, I'm just even going to make a new lines in here. Okay. I'm going to do new code, right? And then I'll do like DeepSeek, right? And then I'm going to copy this thing and put it in here. See, I only need to change the name of the model. And then I load it. Now I get DeepSeek. Like, do you see how cool this is? Like, you had everything under your disposal. It's so cool. Like, I just tried this yesterday. It just blew my mind. Like, how much stuff you can access for free. This is like, oh, but it has custom code. You can inspect the repository. Maybe, yes, I trust it, I guess. I have to trust it, or I cannot do it. And then, yes?
Training in Hamlet again?
No. This one I'm not training. I'm just loading the model. It's called pre-trained model. Like this place contains so many models that's already pre-trained for you to use for free. This is like mind-blown stuff. I just noticed that a couple weeks ago, last week. Like, this is so cool. Like, I mean, you can use DeepSeek right now on your computer, right? That's Python for you, man. Okay, but this one has error because DeepSeek actually required lots of library. Okay, so there are things about, technical things about it. For example, this one, you have to do more things. So I'm gonna skip DeepSeek for now because it's so new. But I'm gonna try something a little bit more conventional. For example, if you try something that people download a lot, then it should probably work. For example, if I do, I don't know, perplexity. I don't know what that is, but I'm going to copy it and then just change it. I have to do Y. Okay, it's downloading. So it's downloading the new model. Okay. Oh, so this is 5.2 gigabytes, so probably not gonna do it today. It's too big. Okay. So something like this, like you can go through the models and then see what you want to use, and then just try it out. And then there's so many things you can try. So the one that I try is called the OpenAI GPT-2, right? So that's smaller model. The newer one is actually pretty huge. So Feel free to try it on at your own time because sometimes it takes a while to download it, okay? All right, so I'm gonna skip the text generation to something that you can do with Transformer. This one called questions and answering, okay? Let's try what it is. Let's try to see what it does, okay? Okay, and this one, you have to give the model the context. For example, you can copy, like you can just copy like a snippet from Wikipedia and then ask the model to find the answer in the context. For example, like this one is the Hugging Face, I guess, history. And then I ask the model, like, who are the Hugging Face founder? And the model is going to answer that it's extracting the answer from the context at the position 37 to 70, which is this guy, which is correct. Okay, this is pretty cool, right? So then if you want to try something else, you can go to Wikipedia, okay? And then just copy any text, like any random facts in here. Like for example, I can do this, right? Just copy random facts in here, and then ask the model the questions. Like I'm gonna copy the facts and do that, right? And then maybe I can ask the model, what is USS Congress? Okay. What is USS Congress? Like that. And then I get the answer. Like it's a heavy frigate, like which is correct. Okay, so the model has been trained to look for answer in your context. Okay, that's pretty cool, right? Okay, and also feel free to, if you want to try on your own, feel free to explore a different model. For example, you can go to Hugging Face library, and then look for questions and answer filter. So you do like questions and answering, question answering. What I want is this one right here, question answering. If I click here, then these are the models that I can use for question answering, which is a lot, right? There's so many models. Usually you want to see the one that has a lot of download. So the one that I have, it has 1 million downloads per month. So that's probably the popular model. Okay. Okay, so next up we're going to do sentimental analysis. So this one is going to tell you that if the sentence it has positive or negative sentiment. Like usually you want to do this like comments, like you can use it to automate like the comments to see if like your product has positive or negative sentiments, and you go through the comments using like this type of model, for example. And I know that in the like Wong Nai, for example, they use this type of thing to determine like the rating. Like if you comment in Wong Nai, then you actually know if your comment is positive or negative using this type of model. Again, this one takes some time to download, right? So. Wow, my computer, this one doesn't download anymore. Okay, so if I say I love Transformer, then the model predict the positive sentiment with a score of 97%. So this one pretty good, right? But then if I say I hate Transformer, then it's gonna say negative, something like that. So you can try different things, like I don't think I like you that much. Then I don't think I like it that much, then probably gonna say negative, something like that. So pretty cool, right? That's called sentimental analysis from the text, okay? Okay, and the next stop is gonna be fill mask. So another task you can do is let the model predict whatever the missing words is. It's called the mask. Okay. So for example, if I can say that the answer to the universe is, and then I want the model to predict whatever this is, it's going to tell me a lot of things, but it's going to say I guess the most confident answer is called no. I don't know if that's the right one, but let me try something else that's more like the sky is, right? The sky is, and I will say the sky is clear. The sky is clear. It's actually, the sky is blue. It's actually not that. It's the second common one. The sky is clear. It's actually more common. Okay. Yeah. So you can try something else, like the bond. The bond. Let me try something more like academic, like the bond. No, is it happens between oxygen and hydrogen. I would say covalent bond. I don't know if it can do that. Double bond. Okay. Hydrogen bond. Okay, so it's doing an okay job, but yeah.
You write, my name is James, and then it should answer James Bond.
Oh, yeah, okay. My name is James.
And then a comma.
Comma?
Yeah.
Okay, and then I do mask in here. James, my name is James too. No, let's do this. If I say 007, probably should say James Bond, right? No, no, it's definitely not doing that. Okay. Okay, so yeah, it has some limitations, depending on how large the model is, right? So you can see.
Yeah.
I think he says my name is Bond, James Bond.
Yeah,
My name is, okay, my name is Bond. Okay, mass. And then James Bond.
My name is Bond.
Uh, James Bond, okay.
So
My name is James. Oh, there's this one right here. It's actually less confident about this one than the first one. Okay. Yeah, so I mean, it's not perfect by any sense, right? But it is closer than RNN and Ngram for sure, like this type of transformer model. Okay. And for those in Thai, then you can try the Thai model. So actually, this one has been, this one is pretty amazing because this one has been trained through like Wikipedia, Wong Nai, and Pantip, and a lot of places. And you can ask the model to do the Thai language now. So it's doing okay. From what I heard is that this model is about has the knowledge of Thai language about the มัธยม3 no ประถม3เหมือนเด็กประถม3รู้ภาษาไทยประมาณเด็กประถม3ตอบได้ Okay. Yeah, so this is what I have for the language model. So I'm actually skipping the part where I do the training and the inference of the transformer model because I don't have time to prepare. It's quite complicated. But at least, I kind of show you how it works. And then, like this hacking phase is gold mine for those who want to do, like the language processing. This is so cool because a lot of things in here, it's actually offered for, like all of this is free, right? And then you do have the capability of like using all of this in your work. I mean, probably not your work, but in your project, like whatever project you want, you can do like automation pretty easily using this type of model. So yeah, so hopefully you can use some of this in the future. Okay, that would be cool. And I'm sure that there's more that coming in this field. Like the information explode like every year. Like every month there's new things all the time. So we'll see what happens. And then like if you want to try, there's already the model that do text to image, like a diffusion model. It's actually also in here. And you can do that too. Yeah.